Thank you. Now, we've heard a little bit about Gluon today, but I just wanted to justify a little bit about why we think we need Gluon. So, Chris kindly explained some of the details about NVIDIA hardware, and we see that this was kind of the world we were in with Ampere. So, as the hardware was, you had to, for your pipelined loads, you needed to issue the CP async instruction, which handled a small amount of data at a time. So in practice, you needed all of the warps in your program to be actually issuing these load operations. And because they were only loading a small chunk of the data and the MMA was in registers, you needed to synchronize and load them in a particular format. So your map-mal kernel ended up looking like we see on the slide here, where we have 4 warps and each one is issuing loads, they're syncing, they're issuing MMAs, we're looping around, and this just looks a lot like your Triton program. So Triton was in some ways just a really good model for abstracting away the hardware details of Ampere. And in this world, the responsibility of the Triton compiler was really just to decide how to distribute all those operations among the warps, sort of the data that's being processed by those operations. Whereas in the world of Blackwell, things look very different. As Chris has said, we need to have this warp specialization. And this is kind of driven by the fact that loading is no longer done in these small little chunks by each individual thread. It's done by the TMA en masse. And you only need one warp to be issuing TMA instructions to be saturating the unit. And similarly with MMAs, it's reading it directly from shared memory. It doesn't need to read it from registers anymore. One warp issuing MMA instructions can saturate that unit. So what your program ends up looking like after it's being compiled by Triton is that our kind of main 4 warps that we had in the Ampere world is now just processing the epilogue. And that's quite understandable. But we have these separate partitions, these 4 and 5 warps on the slide, that are now doing just loads or just MMAs. And for a simple map-mal kernel, it turns out that the work that's been done by NVIDIA and the rest of our team is perfectly sufficient, and we do generate this code. But as Chris sort of detailed there are lots of different schedules as you get a more complicated kernel, and exploring those different schedules really changes how the performance of the hardware is, because you're trying to really overlap as much as possible all the different operations that you have. And one little bit of extra memory that you can squeeze out that lets you add an additional stage to your pipeline might mean you can hide more of the load latencies, for example. It might mean that you're able to avoid these bubbles that were shown in, and you're really saturating the hardware more and more and getting more of that performance. But implementing these tricks in the hardware level just becomes sort of increasingly intractable, because there's such a wide amount of performance space that we can be exploring, and we don't really want to be overfitting the compiler to just one particular kernel. We want to give expert programmers the chance to explore that themselves. So this is why we're introducing a new language, Gluon, that's kind of, in some sense, it always existed, because it's exposing the details inside the Triton compiler that are sort of mid-level IR that we were optimizing internally. But we're really focusing on trying to expose that in a way that's it's exposing the detail, but it's user-friendly and it's familiar to the Triton users. It's a familiar API, and it's still got the clean syntax that you're used to with Triton. But we're just exposing those hardware details in much lower levels and really empowering kernel developers. Now, of course, this comes with some trade-offs. You're programming directly against the hardware, so it's no longer portable. And it is going to be harder to write. There's going to be a lot more details that you'll have to consider in extracting that best performance. Now, here's a small example of a Gluon kernel, and it's obviously a slide where it's not a real example, but the key thing to take away from this is that it looks almost exactly like a normal Triton kernel. But the most obvious difference here is we have this highlighted in blue, this layout attribute that we're adding when we call Gluon arange. And what this is if you're a Triton developer, you'll be very familiar with it, but it's an extra attribute that's part of the tensor type that actually defines how we distribute the data in that tensor among the different threads in a warp and how those registers within the thread contain the data. And so I've kind of copped out a little bit by making it an argument to the kernel here, but there are lots of different layouts you can choose from. Some of the most common types are block layout, which is basically the ideal layout for doing a coalesced data load, and there's different variants about you can decide how you're going to trade off between more vectorization versus maybe having the data loaded in a better format for whatever operation you're going to do. And there's also things like slice layout, which if you're doing multi-dimensional tensor, it basically just removes a dimension from the layout. And this generalizes, within the compiler, we have this very generic layout system that has been alluded to multiple times throughout the day. And these are linear layouts. And with this framework, you can define a very wide variety of different layouts and really specify almost anything that you want. And what does this give you? This just gives you a lot of extra control that you don't necessarily get with Triton. So with the layout specified for your given operation, it pretty much defines how we're going to lower that into LLVM code. So there's no real heuristic that's based on the rest of your code. You're directly specifying one variable that is involved in how that's going to get lowered. And one of the kind of common pitfalls with Triton is you might have a layout conversion somewhere where the data needs to be represented in, say, an MMA format for your matrix multiplication and a block layout for your load, and maybe that conversion is happening in an inopportune place, and that's really affecting your performance. Now you have direct control over where this happens, and you can avoid having it in those sensitive places. You also have the freedom to explore unusual layouts that you might not necessarily see generated by the compiler. For example, we always try and pick the most optimal layout to load, and maybe in your case, you're doing some particularly funky operation with it, and maybe you want something different. But the next big difference with Gluon is the kind of main killer feature is we have explicit support for manual warp specialization. And what this looks like is a special op within the language called warp specialize. And at that point, when you call that op, it kind of forks the execution of the program. We have what we call the default partition, which allows you to pass tensors, and it's basically the same warps that executes everything outside of the warp specialized region. But you can also specify additional worker partitions, and these actually run a different code, and they can have a different number of warps. And for example, in your matrix multiplication, one worker might be doing your loads, and another worker might be doing your MMAs. And after you've finished execution of all the worker regions, it's going to block and resume execution of your main kernel. Now, once you've got these separate programs running independently, you really need some way to communicate between them. So in Gluon, we're actually exposing the shared memory directly in the language. And now this isn't just a raw form of the shared memory, it's actually what we call memory descriptors internally. And these have a layout associated with them. And that means that when you compose them with your tensors in registers, the compiler can figure out how to do all these complicated load and store operations, for example. If you're doing something that might use SD matrix or LD matrix, our compiler will generate that automatically and figure out the best instruction sequence. We also have support for dynamic indexing on just on the leading dimension, but This allows for explicit pipelining and all those various optimizations that you might want to do. The other main feature is that we expose hardware intrinsics that allow you to directly program against the tensor cores and other various hardware features coming out in the latest generations. So, for example, Blackwell attention has been a major driving force behind the Gluon effort. And so I've shown some of the examples of the things that we're exposing for Blackwell. We're exposing the tensor memory that Chris mentioned, the 5th generation tensor core MMA operations, which are actually asynchronous operations. So we're exposing these extra complexities that you don't necessarily get in the TL dot, but that gives you the freedom to write the more complicated schedules that you see in the warp specialized code. Now, once again, that does mean that you need to have understanding of the particular hardware generation, and we don't have the generic TL dot within Gluon because that involves quite a complicated transformation from everything being in tensors to you need to feed data through the shared memory. So this is all handed off to the programmer to control. And I'm at this point going to hand you over to Jeff to talk about a case study on the flash attention kernel that kind of motivated this development effort.
All right. Yeah, so thanks, Peter, for the quick introduction to Gluon and like kind of the high-level aspects and important features that the language has over Triton. So like there's been a lot of talk on like flash attention on Blackwell throughout the conference so far, so it's really good that other people have just like taken parts of our talk for us so we don't have to talk about it. But yeah, flash attention on Blackwell was like the motivating use case for building Gluon. And just to start, like I kind of want to give an intuition on like why. So here's like kind of a, I don't know what you call this diagram. There's a diagram of like what you would write flash attention in Triton. So you have like an outer loop that has one or more iterations depending on if the kernel is persistent, and then you have your attention inner loop, which is like a dot, your online softmax, and another dot. And you've got like loads and stores, you know, in the prologues and epilogues and so on. So this is like what you would write, and this is what like tutorial 6 looks like. And of course, if you have causal masking, you might have 1 or 2 inner loops depending on whether or not you've decided to split the loops into 2. But anyways, this is like kind of like what your flash attention looks like. On Blackwell, with warp specialization, you actually want something that what looks like this. So you've got 1, 2, 3, 4, 5, 6 partitions. That's 6. You can kind of think of each partition in a warp specialized program as being like an actual CPU thread, where each thread is just like executing concurrently and doing completely different things. And they're communicating over memory and like mutexes, and in this case, they're called M barriers. And so you have 6 partitions that are all doing different things. You have one that does loads, one that does the MMAs, and then actually you also want to subtile the computation along M. So you've broken up your tile into 2 M subtiles so that you have 2 partitions doing softmax at the same time. And that's like a detail that is like one, the question is like, does the compiler do the subtiling, or do you do that in your actual source code? Who knows? And then if you look at this along the time axis, right, so you have each of these 6 partitions doing stuff, and here you kind of look at how the pipelining actually works. So you've got the loads coming in for your Q and your K, and then once the loads are there, you can start issuing the MMAs. And of course, because we've broken up along M, there's like Q0, which is the top half, and then there's like Q1, which is the bottom half. And so once the MMAs start completing, you can start your softmax. So here's like the actual, like what I've highlighted here is the actual like key part of Blackwell attention is like the softmax, especially the exp, is always busy. Like it's running 100% of the time. And that's exactly what you want. For float 16, it turns out to be fairly tight, that like the MMA is like takes almost as much time in terms of the critical path as the exp, but the exp is still just barely the critical path. And so the trick with this like fancy M subtiling and this like warp specialization of everything is to keep that exp unit as busy as possible, because that's the bottleneck. And it's really difficult to achieve this with software pipelining. And I think Chris's like scribbles on his diagram demonstrate like why that's hard to do. It's simply because like, well, one practical reason is PTX, the low-level compiler, will order the instructions like however it wants, so you don't actually have that level of control at a level above PTX. The second reason is like that's actually just hard, and you can just rely on the warp scheduler. There's a couple of tricks. There's a lot of tricks to actually get the X unit to be busy 100% of the time. One of them is tensor memory. There's only so much tensor memory in an SM. So you have 512 columns. Each column is one 32-bit cell, and you have 128 rows. But it turns out that you actually want your actually, I'm not sure if those numbers are right. Anyways, the point is that just the accumulators for the dots will take up all of the tensor memory. But in order to make the PV-MMA to be faster, you want the left-hand side to be in tensor memory. So the 5th generation Tensor Core MMA instruction supports the left-hand side in tensor memory, and then you'd have this fancy lifetime management where sometimes the memory is not being used and you can put P in there, and sometimes it's not, and that requires synchronization between all of the different warps. And that's a kind of decision that, from the compiler perspective, you're essentially deciding between using more or less memory and synchronizing or not, overlapping or not overlapping certain compute. And it's very difficult for the compiler to analyze this and figure out how to actually insert the right synchronization and which parts of the program can overlap or not. It turns out that certain MMAs are not actually running at the same time with other MMAs, and you can do this in a way that it doesn't impact the critical path. So you can kind of pass ownership around the different partitions of this QK buffer between the QK MMA and the left-hand side for the PV MMA. So I don't know how readable that is, but kind of give an example. I don't know what just happened. But to give an example of how this is achieved in Gluon, so a lot of the things that we've done as part of building Gluon was making the Triton front end more powerful. So the Triton front end is used for both Triton Lang and Gluon Lang. But one of the things that we've done is you can build abstractions, you can build high-level abstractions in Gluon. So here's an example of what I call Zig style generics. And Zig, if you're not familiar with, is this cool new language on the block that has really nice metaprogramming. So you can define a channel type, which can be either a shared memory channel or a tensor memory channel. And for those familiar with Cutlass, this is the pipeline struct that is basically a circular buffer, and it has M barriers inside of it. And so you have this generic channel abstraction, then you can use that to acquire. So here's the example of what the correction partition which is doing, and all this correction partition is doing is loading your accumulator, multiplying it by the scale factor, and storing it back into tensor memory. So we acquire the accumulator, and in this case, you actually want to acquire this first, because it turns out it's not, this acquisition is not on the critical path. The acquisition, or waiting for the softmax partition is on the critical path. So actually the order in which you do these M barrier waits actually does matter. So the compiler doesn't know that, but we know that because humans can read a profile, right? And then you load the alpha out, and then we actually subtile the correction here. So the correction is there's only so many registers available, and one of the trade-offs with warp specialization is you are using more registers just because you have more warps flying around. So in this case, you can subtile the correction by loading the tensor memory tile one slice at a time. You load it, you do the multiply, you store it back in. In this case, Gluon actually has an abstraction built entirely in the library for accessing the float 32x2 instructions, the vectorized instructions on Blackwell. And you can subtile this essentially as much as you want up to a limit, because the correction is not on the critical path. But that's why it's warp specialized, is to take it out of the critical section. So this is kind of how the code looks in practice. And it looks a little complicated, but in reality, I think this is fairly clean and intuitive. And there's a whole bunch of other tricks you need to make Blackwell attention be performant. You need to put the loads of K and V on the same circular triple buffer, and that's because there's only so much shared memory. Ownership management of shared and tensor memory is non-trivial, and in fact, you can if you look really closely, you can discover that certain M barriers are redundant, and you can remove them, and each one of those that you remove is 0.5%, and those add up over time. There's many decisions to be made versus subtiling. Do you subtile this arithmetic computation? How much register budget do you give to the softmax versus the correction partitions, and so on? There's another trick, which I didn't call out, which is you actually want to subtile the MMAs as well. So when half of the softmax is done, you can kick off half of the PV MMA. Start that early, and while the rest of the softmax is running. And the other factor is like, this is the optimal schedule only for like long context length, like maybe 4K, 8K and above. And the reason is because of this inner loop steady state. So we essentially assume that the inner loop will like reach steady state for a certain amount of time, and the prologue and epilogue of the outer loop can be completely hidden by the length of the inner loop. If your sequence length starts to get shorter to like 2K, 1K, 512, suddenly this inner loop like either doesn't reach steady state, or it like doesn't reach steady state long enough to hide your epilogue. And the optimal schedule starts to look completely different. In this case, we have like six partitions. The Thunder Kitten's Blackwell attention kernel actually does a very different schedule. It's like arguably simpler, but it performs better at lower context lengths. And if you're down to like only one or two, or like a handful of inner loop iterations, you may as well like completely unroll it and then actually do a separate schedule just on the outer loop. And so when you think about generating this automatically from a compiler perspective, like the compiler doesn't know what the sequence length is because it's kind of just that's like a dynamic, it's a dynamic shaped kernel. The sequence length is not baked into it. And you can say, oh, well, we can auto-tune the schedule, right? And that assumes you have some kind of knob in the compiler that you can crank up and down to change, how the scheduling heuristic works. And also assumes that you want to build auto-tuning into the Triton compiler, all of which is possible, but honestly, it just sounds like a lot of work. So there's like a lot of like engineering trade-offs here. Like you can do all these things in Triton. You can do all the compiler magic. It's a research problem. Automatic warp specialization is like not a solved compiler problem by any means. So, but Gluon is, like Peter said, something that like has largely already existed. It's the Triton kind of backend code generation layer, linear layouts, and all that stuff. And all we really did is like we take the same front end that already exists. We made it a bit nicer so we can build abstractions, and we slapped it on top of the front end. We wrote attention, and the numbers come out pretty good. So this is on GB200s. Like, I'll note that like this is specifically the OpenAI GB200s, which do manage to maintain 2 gigahertz during the like steady state execution of the kernel, which is not true for all B200 systems. Sometimes they drop to 1.8 gigahertz, and we get numbers that are like fairly comparable to cuDNN. I could not figure out how to get the float 8 numbers on cuDNN. I tried to use cuDNN front end. But if someone has float 8 numbers, they can fill in those blank boxes. And so the question is, like, is Triton dead? No. And the reason is simply because like people still want to write Triton and get good performance. And for a lot of like, even on Blackwell, for a lot of like typically memory-bound style kernels, the software pipelining does really well, and the automatic warp specialization that Triton does also like works fairly well for a lot of the cases. And the gap can either be 0 or even negative for certain kernels. The Triton compiler is actually pretty good in many, many cases. The other reason why Triton is not dead is like you wouldn't write a Gluon source generator, right? You don't want your source generator to like manage shared memory, pick optimal layouts, and like do automatic warp specialization, like all these things that you now have to do by hand as an expert programmer in Gluon. You don't have to do in Triton. And so like you wouldn't write a torch compile backend for Gluon. That would be extremely non-trivial. You essentially would be reinventing large aspects of the Triton middle end. And also, like writing kernels in Gluon like inherently has a downside. And so when you look at a kernel that could be faster when you write it in Gluon, there's like the other side of the equation of like, okay, like how much engineering time do you want to invest in that? Like the maintenance burden is higher. If you need to change the kernel in 2 weeks, like it's easier to change the Triton one than the Gluon one, and so forth. And so like it really is just another tool in the toolbox for getting more performance for the workloads that matter. The other like longer kind of horizon answer is like Gluon directly benefits Triton development in many ways. The easy one is like you can now write unit tests for the Triton backend in Gluon instead of in these like funky MLIR strings. And as we write more and more Gluon kernels, this can then feed back into how we develop and improve the Triton middle end. So NVIDIA is actually still investing a lot of work into improving Triton automatic warp specialization. And this is something that we expect to get better over time and like maybe even close the gap with Gluon. It's just that compiler code, especially as like the number of degrees of freedom of the kernel and the hardware starts to increase, the compiler moves a lot slower because you have to like think about abstractions and build them, and C++ code is hard to edit. Yeah, that's it, I guess.
Okay, sure. So are there any questions? Yes. Go on.
I was just curious, would you be able to generate Gluon code from Triton code? Like take the sort of middle IR and like put it back into Python?
So as it happens, we have a way to translate Python code into Gluon code, just as a sort of experimental tool. I think in theory, from the IR level, it should be possible, but there is a slightly lossy conversion that happens there. So I think it should theoretically be possible, but it's not something we've looked into.
Yeah, could be useful for like a optimization starting point, right?
Yeah, definitely.
That's exactly the idea.
Yeah. Any other questions?
Hey, what's the development time comparison with QDSL, like between Gluon and QDSL?
I mean, I'm obviously biased, but I personally prefer Gluon. So like QDSL, I would argue, is lower level than Gluon. For example, you're not restricted to power as a 2 for the tensor dimensions, and the layout system is like more expressive, but also more, you can express more things in it because it can handle non-power 2 dimensions, but it's also like, as an abstraction, harder to manipulate and understand. And I also personally think that like the Qt DSL style of like in register tensors where you have to like unroll the loop is like frankly fairly awkward. And another aspect of like why I think Gluon is easier than Qt DSL is like there is actually like an abstraction layer. Like the compiler will handle a lot of stuff in terms of like synchronization, inserting barriers, and shared memory. And I also think that like the Cutlass, I don't know why QTSL inherited the like Cutlass naming scheme with like T, capital C, lowercase r, S, 0, 1. I think that actually contributes a lot to why QTSL code is like hard to read and write. But I personally think that Gluon is like slightly higher level and is easier to write and feels more familiar if you are familiar with Triton.
Thanks. Maybe a follow-up question on, did you see any changes required for the scheduling for Flash Attention 4?
We haven't implemented Flash Attention 4 in Gluon.
Oh, okay, thanks.
Yeah. But my understanding is that Flash Attention 4 basically started from like the Cutlass kernel plus some tricks from the QDNN kernel and basically ported it into QTSL. And then they added all of the like masking tricks and exp approximation afterwards.
Yeah, sorry, go ahead.
I wonder if there is other hardware support, like a non-NVIDIA or even non-GPU hardware in Gluon.
So non-GPU, I guess, is theoretically possible because we have Triton CPU that uses the same middle-end expression. But we do have AMD actively working on their Gluon backend as well. Basically, anything that has the Triton GPU extensions for their hardware could be implemented in Gluon because we have these hardware intrinsics. So yeah, anything is possible. It just, we don't quite have the same plugin system that we have for adding sort of like the TL.extras modules automatically into Gluon, but these things could be developed reasonably straightforwardly.
Yeah, our question is it possible to make the different schedulings as part of the auto-tuning system? Because OpenAI has this GB200, but say others don't have this hardware, and they want to test other scheduling strategies.
So this schedule is actually like what you would do on a regular B200. It's just like it happens to be faster on GB200. I haven't like done the math and checked if on our specific systems whether you end up with a slightly different schedule. In terms of like, could you auto-tune the schedule in Gluon? I mean, if you did enough metaprogramming, you could. And the question is, could you auto-tune it in Triton? I know a lot of people have talked about like doing auto-tuning inside the Triton compiler, and I think the reality is like it's possible, but it's like fairly impractical to integrate into like existing kernel development workflows. One is because like you essentially have to like expose a knob or a step in the compilation process here, and anyways, you can do it, but it's not super practical at the moment.
Thank you.
Yep.
All right, let's thank the speakers again. All right, thanks a lot, guys.